Welcome to our talk on BlankIt library debloating. I'm Girish. I'll present the first half and then hand it over to Chris. Modern software relies heavily on libraries that are often built for supporting a large amount of functionality. In a given application, however, only a small amount of such functionality may get used. For example, user programs in Ubuntu desktop use only 10% of shared library functions. A latest article from Naked Security describes how open source libraries are a major source of application security flaws. And many libraries are written in C++ for performance and also historical reasons. C++ lacks memory safety and are prone to vulnerabilities which are exploited to create many attacks. glibc, which is most prevalent, has more than 100 vulnerabilities listed while creating this slide. And the top 5 are convincingly severe. Moreover, glibc is a mine of ROP-JOP gadgets that manipulate return address and jump targets, creating an illegal control flow. These gadgets can be stitched together to create semantically valid and Turing-complete malicious attacks. Although known vulnerabilities are patched and remedied, new future attacks can be built over these gadgets. Hence, reducing the quantity and expressiveness of such gadgets, in other words, the attack surface, especially for libraries like glibc, is one of the key contributions of BlankIt. Debloating is downsizing the amount of unwanted code that is available for constructing an attack. Current security debloating approaches can be classified into two categories. Conservative ones that remove only those functions whose removal is deemed safe, example piecewise compilation, or aggressive ones which can break soundness and can lead to crashes, for example razor or chisel. Also, in terms of gadget reduction, these approaches debloat only about 60 to 80% of the attack surface and also do not handle glibc. In this work, we propose BlankIt, and the idea is to dynamically bring in only those library functions that are required at the application call site and then purge them after the return from the library. At a high level, at program start, BlankIt removes all the library code. When the application needs to call the library function, for example, function foo, BlankIt predicts and links the required functions for the library call, and when the call returns, all the library functions are delinked. In this way, BlankIt on average reduces 97% of the attack surface. What else BlankIt does? Current defense mechanisms that involve hardware such as ASLR and DEP cannot protect against advanced control flow hijack techniques like return to libc attacks. To defend and prevent against such advanced techniques, mechanisms like control flow integrity, memory safety have been invented, but they are still limited. BlankIt can augment these advanced techniques like CFI and CPI to overcome some of these limitations. CFI is a mechanism that attempts to restrict the program execution to legal paths only. However, computing a fully precise CFI is intractable because of limitations in pointer analysis, presence of set jump long jump, and mostly the inherent inability to distinguish between a legal and illegal dynamic control flow. Memory safety is a defense mechanism that prevents memory corruption by verifying the correctness of memory operations. While memory safety techniques like softbound plus CETS can prevent almost all control flow hijacking attacks, they incur overheads greater than 2x and hence are impractical to deploy online. Code pointer integrity uses memory safety only on pointers that can directly or indirectly modify control flow, thus lowering the overheads of a full memory safety mechanism. CFI and CPI are limited in handling control flow bending attacks, which is a generalization of non-control data attacks. Non-control data attacks lead to illegal control flow. For example, changing branch outcomes, corrupting function pointers, switch variables, etc. CFB, along with a dispatcher function can easily make CFI ineffective. Such dispatcher functions are commonly available in glibc. CFI also does not handle certain types of privilege escalation attacks. CFI and CPI must be augmented with other defense mechanisms for these specific attacks that fall outside their scope. New attacks undermine the current best practices of defense mechanisms, but BlankIt can tackle many of these limitations. For example, in this code derived from the related work, a user's credentials are verified with an input key in function service, and the result is assigned to the variable user. Input variable SumInput can be manipulated by the program user, causing a buffer overflow at line 6 and lead to superuser access at line 8. This attack is not handled by CPI or the latest CFI like PyCFI or MuCFI. But in the case of BlankIt, the call superuser function is not predicted and the attack is detected. Apart from the common assumptions of trusted base, we assume application source is trusted and we target external libraries by treating them as a source of threat. Please refer to our paper for more details on the threat model. Normally, an overflow vulnerability can be exploited to jump to an arbitrary address within glibc. But with BlankIt, since the library functions are wiped out, jumping to an arbitrary address results in a fault. In BlankIt, the set of functions that can be read through the vulnerability is reduced by the prediction mechanism. Hence, a highly accurate yet lightweight prediction framework is critical to BlankIt's success. The predictor must distinguish between legitimate dynamic control flow and an illegitimate counterpart. If a library function is non-divergent, all dynamic calls of the function will result in the same call chain, making prediction trivial. A function is non-divergent if every call site within a function post-dominates the entry block of the function and the called function is itself non-divergent. In glibc, we found that 737 functions, roughly 27%, are statically non-divergent, and remaining 1985 functions need dynamic predictions. For the divergent functions, we contend that the reverse dominance frontiers of the arguments passed to the function can decide the control flow within the callee. For example, in the previously shown privilege escalation attack, the input to function service on line 18 in access service has one argument key which is defined at RDFs B1 and B2. If B1 is executed, then key has admin access, and if B2 is executed, it does not. The control path in library functions can diverge because of the various values of the arguments from the same RDF. For example, math library functions like square root and exponential have different call chains depending on the range of the parameters. Hence, we include the argument values in our prediction framework. We selected decision trees for prediction as they can be easily embedded into the application as few predicates. We profiled to create the training data with features consisting of application call site, callee name, RDFs, and the arguments passed to the library call. Scikit library is used to generate the decision tree, which is then embedded before the application call site and optimized through LLVM. For the previous example, the decision tree learns that on a call to service from function access service, call superuser is called only when RDF B1 is taken or key is less than 750. I will hand it over to Chris to walk everyone through runtime and results.
All right, I'm Chris. So let's get into the runtime. What we've done is take Intel's pin framework, which came out in PLDI in 2005. We built a pin tool with it, which allows us to instrument trampolines at function granularity at near native run speed. At a high level, a program running with BlankIt will be constantly predicting upcoming library calls, loading and unloading the library functions that are needed, and handling mispredictions. Let's consider unblanking first, where the runtime system loads a library function. We can follow the arrows in this diagram, which show what happens when malloc gets called while BlankIt is running. Following arrow 1, the call to malloc hits our trampoline. This jumps along arrow 2 into our probe copy code. Focusing on the red pseudocode on line 7, you can see that it performs a mem copy. This will copy all predicted functions, including malloc, back into memory. Arrow 3 returns to malloc and it executes. Arrows 4, 5, 6, and 7 repeat the process when malloc calls mmap64, and arrow 8 is our return. Now let's consider the predict and blank steps together. The takeaway here is that a prediction precedes every library call that our application makes. That's when our runtime system will blank the last set of functions. As you can see, arrow 1 jumps into a probe BlankIt predict call, and the blanking happens at this red pseudocode on line 5. The prediction is stored, and after we return on arrow 2, we make the library call. In this case, it calls free, and if the prediction checks out, then everything's fine. If not, we have to handle it. When the call flow does not match the prediction, there are different ways to handle it, each appropriate to different circumstances. For example, we can kill the process, restore from a previous VM checkpoint, use forensics on a core dump, or run an audit thread. We looked most closely at how parallel audit threads could be used with BlankIt. In this scheme, there's a parallel audit thread that handles mispredicts. When one happens, it loads the library and calls the mispredicted function within Valgrind's vimcheck. There are 3 cases we have to handle. Library calls with scalar arguments are the simplest. At runtime and on mispredict, the arguments are passed directly to the auditor. Pointer arguments require the auditor to track metadata of the pointer start address, type, and size. And library calls that maintain state cannot be independently repeated by mimcheck with just the input arguments. These calls have to be identified prior to runtime, and mimcheck must repeat all calls needed to recreate the state. To test the viability of this work, we use a standard desktop CPU with 32 gigabytes of RAM. We tested with a standard benchmark suite, spec CPU 2006, and to showcase BlankIt working on real-world applications with known security holes, we used Nginx and Sshd. Our main software stack included Ubuntu, Pin, and LLVM. We looked at performance, prediction accuracy, and security. What we found is that for CPU-bound processes like those in spec, BlankIt runs with about 18% overhead, and 16% of that is due to just glibc. Prediction accuracy averaged 94%, and ROP gadget reduction was 97%. In Nginx, the max overhead was about 10% total, but with 100% accuracy and 99% ROP gadget reduction. In Sshd, runtime overhead was negligible in our experiments, with 95% prediction accuracy and 98% ROP gadget reduction. This graph gives you an idea of the performance on spec. The x-axis shows each of the benchmarks, the y-axis shows normalized slowdown. The 3 bars for each benchmark are the native run, which is the baseline, BlankIt running on only glibc, and BlankIt running on all libraries. In most cases, the middle and rightmost bar are near equal. This is because glibc accounts for most of the overhead we see in spec. Again, there's about 18% average slowdown here on that 3rd bar. We've termed one of our optimizations lazy blanking. The idea is to keep the last set of executed library functions in memory so that if the subsequent library call invokes them again, they're already there. This table shows how much worse several of the benchmark's performance numbers get when you don't use lazy blanking. So the biggest difference is HIMR, which is 4.61x slower, and GCC is about 1.05x slower. This table shows BlankIt's prediction accuracy for Nginx and Sshd. You can see that Nginx's accuracy when serving the Wikipedia HTML homepage is 100%. The training was on a simple GET request to a site under construction page. The worst case accuracy was a test case for Sshd with 95% accuracy. We trained on a remote shell script that echoes hello world back to the client. The test case, commands 100, was more complex. 100 parallel processes were creating and changing directories, writing and reading from a file, and sending data back to the client. We looked at multiple security metrics, including a reduction in mapped library functions, ROP gadgets, and glibc functions with known CVEs, as well as a measure of gadget quality without and with BlankIt. You can see that we achieved around 90% or better code surface and glibc CVE function reduction, and the ROP gadget reduction was 98% or better. And gadget quality improved about 25%. Though Sshd did not degrade, Nginx ran slower with BlankIt. In one set of experiments, we varied the time of our Nginx workload but kept the payload constant. The worst case slowdown was 1.09x. We also varied the payload size but kept the workload duration constant. The worst case there was 1.04x. And all slowdowns for Nginx are under 10%. We'll walk through the Nginx attack example that shows how BlankIt could be a useful defense mechanism. This is figure 7 from Evans and others at MIT on their Control Jiu-Jitsu paper from CCS 2015. Both return statements invoke a function pointer called context output filter. It passes 2 arguments. One is part of the context struct itself, and another is an input pointer. The authors call this an argument corruptible indirect call site. The context object and variable in can be corrupted via some heap vulnerability. In other words, this function pointer and its arguments can be corrupted. So the attacker just needs to point to a useful function, and figure 8 shows exactly that. So here Nginx execute proc takes 2 arguments and invokes execv with data from the second argument. This allows for arbitrary code execution. The problem with this kind of attack is that defenses like control flow integrity simply are not built to handle it. They can't recognize the initial heap corruption, and they can't recognize when the function pointer goes off in the wrong direction. BlankIt, however, offers some protections against this. Invoking Nginx execute proc will invoke BlankIt's trampoline and prediction checks. If it's not been predicted, then the mitigation phase kicks in to handle this attack. There's still a lot to explore, so we want to understand how we can scale beyond libraries to full applications. And the mitigation component also deserves a closer look. We explored audit threads, but applying forensics on core dumps is an interesting path forward. And future optimizations include improving hoisting of BlankIt calls outside of loops interprocedurally, as well as dynamic invariant discovery to further limit blanking and unblanking calls. Now to conclude, BlankIt debloats practical, common, and CVE-ridden libraries, including glibc and libstd std++. It has a huge security benefit, reducing 97% of ROP gadgets. In 15 out of 17 spec benchmarks, it made the remaining gadgets even harder to work with. It offers protection on real-world software, and the prototype has a practical overhead of about 18%. All right, I hope you have a chance to read the paper, and thank you for listening to the talk.